Model specification. Okay, let us now consider a number of modeling issues here. Actually, three. First, choice of explanatory variables, the Lorentz independent variables or regressors, and choice of functional forms. And we look at an issue of multicollinearities. Essentially, this choice of explanatory variables or choice of functional forms, in principle, they should be determined by economic theory. There's a few things that we got to be careful about in doing so, which we will go through step by step. Okay, first, choice of regressors. It somewhat depends on the purpose of the models. Whether you want to use model for prediction or you want to use the model for causal analysis. So prediction, what do we mean? So here our main purpose is to predict value of dependent variables. And this predictive analysis is actually becoming increasingly popular with big data. If the purpose is to do predictions, so now our right-hand side variables, our regressors, we should choose those variables that are highly correlated with the y-dependent variables in order to achieve a high R-squares. Okay, so that's for prediction. For causal analysis, so now our dependent variables y, our explanatory variables x1, x2, x3, x4, so on and so forth. So we will be interested in understanding holding say x2, holding all the other variables constant. How does x2 affect y, or the marginal impact of the x2s on the conditional mean of y? Okay, so we want to look at this causality. Causality goes from x to y. So this is frequently used. It's important for policy work. We want to evaluate a particular policy. In such case, it's important to include all relevant variables so that we can be sure that all the other factors are held constant. Okay, what's the difference between this wording? You might feel a little bit abstract about the difference between prediction and the causal analysis. So let's look at the examples for concreteness. Suppose the true models is this: y is equal to beta 1 plus beta 2x plus beta 3z plus e error terms, and all our modeling assumptions are satisfied. And particularly, E is exogenous, strictly exogenous. And further, also, let's assume that x and z, they are correlated. So x can predict z. So conditional mean of zi, conditional mean of z, conditional on x is equal to gamma 1 plus gamma 2 xi. Okay, so we can use x to predict z. So x and z, they are correlated. So the causal effect of x on y would be the marginal impact. So conditional yi, xi, zi is equal to beta 1 plus beta 2 xi plus beta 3 zi. So partial differentiate, this clearly D is partial differentiate this conditional mean of y with respect to xi, holding zi constant, holding this constant. Okay, so we got beta 2. So now beta 2 has a causality interpretation. It captures the causal effect of x on y holding z constants. So to estimate beta 2, this causal effect correctly, it is very important to include z in the regression. Okay, suppose not, so we omit z. Then we are estimating this. So conditional. Okay, let me write out the two models. Okay, yi is beta 1 plus beta 2 xi plus beta 3 zi plus ei. So conditional on xi. So now we omit z, we ignore z. Okay. So e condition yi xi condition ei conditional xi. And now I hope you are comfortable with this operation, expectation operation. You think that this is linear operations, okay, on both sides of the equation. So beta 1 is constant, so it doesn't depend on xi. Beta 2 xi. So when we conditional xi, you can think of this as a random variable, but we conditional on it. That means intuitively, that means we treat xi as a constant. So xi is here. Plus third term beta 3 constant. In zi, so expected value of zi conditional xi plus the last terms, error term, so is expected value of ei conditional xi, and this is 0 by assumption. We assume that xi is exogenous, or we assume that xi is exogenous to ei. So this is 0, will disappear. And we know that this depends on this is equal to gamma 1 plus gamma 2 xi. So that xi can predict zi, or xi is correlated with zi. So let's plug this one in. So we have beta 3 times gamma 1 plus gamma 2 xi. So we have xi here, we have two constant terms. So let's rearrange the terms. So beta 3 times inside, beta 3 times gamma 1. So constant term is beta 1 plus beta 3 times gamma 1 plus xi. So we have beta 2 plus beta 3 times gamma 2. So beta 3 gamma 2 times xi. And that's this. Okay, so now we partially differentiate this one with respect to xi. So this constant term drop. So xi is a power function xi. We know that now the partial derivative is this. And you notice that this is not the same as beta 2. Okay, there's an extra term here. So when we regress y against xi, get the coefficient estimate of beta 2 plus beta 3 gamma 2 is not the same as estimate of beta 2. Does not give us the causal impact, the estimate of causal impact of x on y, because it includes these terms. These terms is the effect of x on y through z. So when x increases, this affects y directly. We use different color. When x increases, it affects y directly. It also affects z through its correlation with z. Then z affects y. So now we have if we omit zi, we regress y on x, we pick up two effects. One is the causal effect of x on y. The other is kind of intermediate secondary effect that operates through its correlation, x correlation with z. Okay. So we cannot interpret this as a causal effect. But if our purpose is for prediction, then that's fine. We can still just regress y against x and predict y. Okay. So I hope it is clear to you what is the causal analysis and what is the predictive analysis, the difference between them. Right. So if our purpose is to do a causal analysis, we want to find the causal effect of x on y, we need to include relevant explanatory variables in. Otherwise, we can suffer from what is called the omitted variable bias. What is this? Let's have a look. Okay, suppose the true model is this model. So we have two variables x and z, and certainly all the assumptions we needed are there. And we ignore z for whatever reasons. For example, maybe because we do not have data for z. Okay, then estimate this model. That means that, so now I'm denoting error terms as E tilde. That means we leave z into the error term. So E tilde I is beta 3 times zi plus the original EIs. Okay, and let's see whether our estimate of, we regress y against x, whether our estimate of beta 2 here, can we do a correct estimation? So if you recall the formula that we have for the OLS explainers, simple linear models is this. And we can bear in mind our true model is this. EI. So we can plug this one into here. Then we can write out beta 2 star. Okay, we are using different notations for these estimators. It's equal to beta 2, a little bit algebra, plus a weighted sum of the error terms. Okay, where weight is this. Okay, and so our E2, our E tilde, this is our E tilde. Alright, so we plug this one into here, then we got this. Okay, taking expectation of B2 star conditional on the data, all data. So we can, these terms EI x z is 0 by assumption. That's our strict exogeneity assumptions. So disappear. So we have this one, and plug this one in. I won't show you the step-by-step details of the algebra, but if you need to know this, you can come back to me. Otherwise, I hope you just follow intuitively. Okay. So plug this one WI into here. We can write this conditional expectation of B2 star as beta 2 plus beta 3 times a term, these terms. And let's look at the numerator here. This is just the sample covariance between the x and y. And here, x bar is average of x. And similar for z bar. Okay, this is just the sample covariance. And the denominator is just the sample variance of x. Okay, and whether conditional expectation of B2 star is equal to beta 2 or not really depends on these terms. Okay, and here we are conditional on x and z, the data, the explanatory variables. We can work out the unconditional expectation like this. So basically, we are applying a law of iterated expectation. The inner expectation is conditional x and z. The outer expectation conditional taking expectation over x and z, average out in a sense. So we get this. And in large samples, we can actually show that. Remember, let me write out this covariance hat of x and z is n-1 times sum of, or we can, in large sample, we can just divide by n, which is 5, okay? Xi minus x bar times zi minus z bar. So as n goes to infinity, this x bar, what is x bar? 1 over n sum of xi. This should converge in probability by law of large number to its mean. This is called mu x. And similarly, z bar converges in probability to mu z. So we can loosely you can replace this by mu x mu z. And then again, law of large number, we say that these terms converge to its expected value. This is just by definition the covariance between xi and yi, and that's the same as covariance between x1 y1 x2 y2 because zi, because we have RID assumption here. Okay. So we see that beta 2 star actually capture two components. B2 star capture two components, beta 2 and beta 3 times covariance between xz and divided by variance of x. And expected value is not the same, so it's biased, our estimator. When we omitted z, our estimator is biased unless beta 3 is equal to 0, okay? And it's not consistent estimator of beta 2. And we can actually work out the bias, which is expected value, conditional x and z, minus the true value. So it's these terms. That's the bias. Okay, so now I hope you see that what do we mean by omitted variable bias. So we omitted an important variable x that affect y. So our estimate of the coefficient x pick up not just the causal effect of x on y, but also the additional confounding effect that operates through its correlation with z, which we omitted. So you see, we can have this omitted variable bias. Our estimator is no longer consistent, it's biased. And you might be worried in your regression. You want to avoid such kind of omitted variable problems. So you might want to add as many variables as possible. However, this is also bad. Doing so complicates your model unnecessarily. You are adding irrelevant variables into your regression. So it might inflate the variance of your estimate because of the presence of irrelevant variables. So it's important that you select your variables guided by economic theory. Okay. Okay, suppose you know that that's your true model. Your theory says that okay, y depends on y is equal to beta 1 plus beta 2 x plus beta 3 z. However, say you don't have data for z. Okay, say for whatever reason z is unobserved to you. Okay, for example, you are looking at, you try to estimate the return of educations, and by looking at the wage, whether education affect the people's wage income. Wage income also depends on another factor, people's capability, which is unobserved to you. Okay, so now you cannot include these people's capability into the regression. So you don't have data for this. That's on the one hand, this is unfortunate. On the other hand, fortunately, you might have another variable that's called QI, which you know can proxy for ZI. That means that it will satisfy this condition. So ZI and XI are conditionally mean independent. So if we condition on QI, essentially it says that if we condition on QI, then ZI and XI, they are no longer correlated. Okay. Remember, like a education and the people's observed capability, they can be correlated. But let's say we have data on IQ. So with conditional IQ data, then there's no correlation. So if this is the case, if we have conditionally mean independent between Z and X conditional Q, then we can include Q as a control variables. Okay, so we can use Q to control for ZI. So our true model is this. So taking conditional expectation on both sides, and I hope now you become comfortable with this taking expectations or taking conditional expectation on both sides of equations. So this now I hope you appreciate this. You appreciate that this taking conditional expectation is kind of linear operation. Okay, yeah, you are doing applying linear operations onto the equations. So beta 1 is constant, does not depend on X or Q or any other sense. And beta 2 constant, XR, we are conditional on XR, which means that we're treating XR as kind of constant, no longer random, we condition on it. And now ZI is conditional XI and QI, plus conditional XI and QI on EI. So now we're going to assume that this is linear function. Okay, it can be nonlinear or maybe square. We have square term, cubic term here, which is fine. Important sense that this does not depend on XI. If it depends on XI, then X and ZI are no longer conditionally mean independent. Okay, so does not depend on QI. It does not depend on XI. So this conditional expectation of ZI, conditional X and Q does not depend on X at all. And this we require that X and Q to be exogenous. So now, given this, plug these two equations into here. This one into here, this one into here. We can have these equations. And now you should see that when we regress Y against X and Q, we can estimate this one, and this one. So now this one, beta 2, B2, does is indeed a consistent estimate of beta 2. However, the estimate of this composed of beta 3 and gamma 2, so we cannot identify beta 3 separately. But that's fine, we are not interested to estimate the causal effect of Z on Y. Okay, this is a control variables. Use the control variables in the case that we don't have data for Z. Right, so important issue here is that we need to choose a model. So now you may be wondering how to choose the models. This task is easy to say than to do, because there's no one set of mechanical rules that you can follow. Here are some tips. So first, you want to be clear about the purpose, whether it's prediction or you are doing causal analysis. If it's causal analysis, make sure you include all relevant variables. If it's prediction analysis, predictive analysis, you want to include variables that's highly correlated with the Y, the dependent variables. And certainly you want to use the guidance of theory. Okay, make sure you use the economic theory. if your regression, you end up in having unexpected signs, x, the coefficient of x is expected to be positive, you get a negative estimate, or the magnitude is very, very big, is unrealistically big or unrealistically small, then this might hint that you have missed specifications in your models. You can also check the patterns of individuals, particularly for what is called heteroscedasticity, which we will look at later in later weeks. You can also perform the significance test. Say x1, x2, conceptually they should affect y. So you want to test the Jones hypothesis whether beta, the coefficients of x2 and x1 are Jonesly zero or not. Okay, you can do this test. You can also check for whether there are outliers, influential observations, and you can also, you might have you want to look at the causal impact of x1 on y, and you have x2, x3, x4. You can estimate this your regression models, say from a minimal specification, baseline specification where there's only x1 in it. Then you add x2, add x3, add x4. And every time your estimate of the coefficients of x1 doesn't change a lot, it's always going to change. But if the change is small, then this may hint that, okay, your estimate of beta 1 is robust. Okay. You can also conduct a test which is called reset test, regression specification error tests, to check. We will talk about this in a moment. Okay, you can also use several criteria to select models, and these are more valuable when your purpose is for prediction. For example, you can check R squares, so which R squares is equal to 1 minus sum of square error divided by total sum of squares. Okay, and certainly intuitively high R square means that your model explains higher proportion of the variation in the data, which is good. So the higher the better. However, a shortcoming of R squares is that it will always increase if you add more variables. So if as the number of variables, you say you have 100 observations in your data, and you can keep adding more variables into more right-hand side variable, more regressors into your regression. Then eventually your k goes equal to 100. Then your R square is equal to 1. Okay. Your regression fit the data 100%. Okay, you can make this happen. So this is undesirable property. So sometimes people, rather than computing R squares, people computing R bar square, adjusted R square. So the adjustments that SSE divided by is degree of freedom. Similarly for the SST, and you want to observe that if you increase k, on the one hand this increases, on the other hand we have SSE divided by n minus k. This increases, on the other hand if you increase k, on the one hand this decreases, so that R square will increase. But on the other hand, on the one hand SSE decreases. On the other hand, the denominator here, k increases, so that the whole denominator decreases. Okay, so this kind of, in a sense, correct for this undesired property of R squares. The more variables you add in, the higher R square you always are going to have, right? However, now you cannot explain adjust the R square, R bar square as my model. Suppose R bar square is equal to 0.8. You cannot say that my model, regression model, explains 80% of the variation in data. It no longer has such kind of explanation because we divided by the degree of freedom. Another two criteria that you can look at is if your model is for prediction purpose. So AIC, so that's the AIC, and you should observe that it's very close to sum of square errors, and it add penalties on the the number of variables, right-hand side variable, number of regressors you include. Similarly for BIC, Bayesian information criteria, or Schwartz criteria. So you want to, if you use these two statistics, two criteria, you want to choose a model that gives you smallest AIC or BIC, smallest value of the statistics. All right, so let's look at the reset test, regression specification error test. It is designed to detect omitted variables and incorrect functional forms. The idea is that, okay, suppose we have specified and estimated the regression model of this, and beta 1, beta 2, beta 3, the OL estimate is B1, B2, B3. From here, we can predict the result, not residual, predict the value of y, the predicted value of y, and then conduct in two artificial regressions. So we want to include this y hat square. Okay, pay attention. You don't want to include y hat itself into the artificial models. So you want to include either square terms or your cubic terms, square and cubic term. You can even include y hat to the power 4, 5, so on and so forth. Then test for the significance, joint significance of gamma 1, gamma 2. So if our model is misspecified or we choose a wrong functional forms, this should be, if that's the case, this should be picked up by this our higher order polynomial of y hat. Okay, so gamma 1, gamma 2, they should not be 0 jointly. So failure to reject the null hypothesis says that the test has not been able to detect any misspecifications. Okay, so we want, so now is gamma 1 is equal to 0, gamma 2 is equal to 0. Fail to reject the null means that our model, we cannot detect any sort of misspecifications. All right, last point we want to look at is collinearity, multi-collinearities. So when data are the results of an uncontrolled experiment, and many of these economic variables, they might move together in a systematic ways. So now we say that these variables are collinear, and the associated problem is called multi-collinearities or collinearities. So there are two cases here. If the collinearity is perfect multi-collinearities, which means one variable is a linear combination of the other variables. So maybe we have value xi1, x1, x2, x3, and then x1 is equal to 2x2 plus 3x3. In such cases, x1, x2, x3 have perfect multi-collinearities. So now our MR5, remember MR5 requires that there is no exact linear relationship among the right-hand side variables, the x. So we cannot do the estimation. Basically here, beta hat, the estimate beta, the betas, x prime x inverse x prime y. Okay, this now, that means that this matrix is no longer invertible. Okay. If instead the collinearity is imperfect, then we can still do the estimation, but now our estimate will lack precision. Okay, to see this point, let's consider the model this one, that's the true models, and we can derive B2, which is the estimate of beta 2, and associate conditional variance, okay, at least, where this R23 is the correlation between x2 and x3. So that's the variance, and we can see that this variance can be big. Okay, so if look at this formula, if there's no variation in xi2, x2, okay, which means the deviation from this mean is 0, then xi2 is constant. We can think that this now x2 is perfectly collinear with the intercept. Remember, we have constant terms. Okay, so this will be 0. We cannot divide something by 0, right? We run into a problem. If x2 and x3 are perfectly correlated, so the correlation is 1. So there's a perfect collinearity between x2 and x3. OLS fails. We cannot do the estimation. Variance becomes infinity. So we divided something by 0, actually explode to infinity. Or if R23 is not equal to 1, but very high, for example, R23 is equal to 0.9, and 1 minus 0.9 we get 0.1, okay, and 1 divided by 0.1 we get 10. So variance increased by a factor of 10. Okay, so this variance will be very large. Our estimate is quite imprecise. So in our regression, how can we detect multi-collinearity issues? First one, you can report the correlation matrix among the explanatory variables. This can be helpful. A high correlation will hint at the potential multi-collinearities. However, you want to know that a low correlation does not necessarily mean that there's no multi-collinearities. Or you can use what is called variance inflation factors. So here, basically, you run auxiliary regressions, regress one of the explanatory variables against all the other. So for example, k, rk, regress xk, say k equal to 1 or k equal to 2, regress x2 against x3, x4, x5, so on and so forth. Compute r squares, compute variance inflation factors, which is equal to 1 minus r squared. Okay, for example, if you get r squared, say let's look at the case equal to the second variables. Okay, r squared is equal to 1, which means that x2 are perfectly explained by constant x3, x4 until xk. And now this variance VIF will be infinity, very, very big. If it's 0.9, then VIF is 1 minus 0.9 is 10. So a high value of VIF points at multi-collinearity issues.